when evaluating a system of linear equations with three equations and three variables, sometimes the coefficients aren't as nice as you would like them to be. For example, if I give you this system, 1.6x minus 0.9y is 0.3z is equal to 2.9 as the first equation, then 1.6x plus 0.5y minus 0.1z is equal to 3.3 as the second equation, and then finally 0.8x minus 0.7y plus 0.1z is equal to 1.5. So now this seems very cumbersome, and finding the solutions to linear systems in three variables is cumbersome in itself, but this just makes it a lot worse. But there's a way to make it easier. For example, if we multiply each equation by 10, what this is going to do, as multiplying by 10 does, is it's going to shift the decimal point over to the right one. So it's going to make all of these decimal values into whole numbers. Right? And therefore we wouldn't have to worry about the decimal problem anymore. It would look more like the system that we're used to with integer coefficients. So let's do that. Let's multiply all three of them by 10 to get our new system of equations. So we get 16x minus 9y plus 3 is equal to 29. All I did was just move the decimal point over 1. The second equation is going to become 16x plus 5y minus 3z here minus 1z here, sorry about that, is equal to 33. And then finally we get 8x minus 7y plus 1z is equal to 15. So now this is our new and considerably much nicer system of equations that we can solve as usual. So the point of solving a system of equations is to pick two pairs of equations and cancel out the same variable. So the first thing we should do is figure out what variable we should cancel. And it seems as though the z is the easiest, because notice that if we add equations 2 and 3 together, the z's cancel out because it's negative 1z in 2 and positive 1z in 3 without us having to do any extra work. So let's pick as our first pair of equations 2 and 3 and add them together. So let's just write this over. So here we end up getting 24x minus 2y, and the z's cancel out, which is what we wanted, and that's all equal to 48, right? So we're going to call this equation 4. Now we have to pick another pair. So since we already got 2 and 3, we should either do 1 and 3 or 1 and 2. Now notice that if we do 1 and 2, all we have to do is multiply the second equation, equation 2, by 3. And then the coefficient in the second equation is going to turn into minus 3, which is going to cancel out with the positive 3 from the first equation. So let's do that. So we'll write equation 1 over as is. So 16x minus 9y plus 3z equals 29. And then for equation 2, we're going to multiply it by 3. So multiply every single term by 3. So 16 multiplied by 3 is going to turn into 48x. Then 5 times 3 is going to be plus 15y. And then for the z is going to be minus 3z, which is what we want. And finally 33 times 3 is 99. So adding these two together, 64x here plus 6x, right? And then the 3z's cancel out, and then finally what we're left with is 99 plus 29, which is going to equal 128. So we're getting some pretty big coefficients here, but you know, it beats the pants out of radicals. Sorry, decimals, which is what we started with. So now these two equations form a linear system in two variables. Oh, excuse me, that's y. Thank you. And so now we can solve as usual. So rewriting these equations, we get 24x minus 2y is equal to 48. And then 64x plus 6y is equal to 128. Now, it seems like the best thing to do would be to get rid of the y because it's got all the small coefficients, right? So if we multiply the top equation by 3, we're going to get a negative 6y on the top. So it's going to cancel out with a positive 6y. So let's do that. So 24 times 3 is 72x minus 6y equals 48 times 3 is going to be 144. And then the second equation we just rewrite as usual. So 72x plus 64x is going to give us 136x. The y's cancel out, and then these two big numbers combine to form a bigger number, which is 272. And then if we divide both sides by 136x, we find that 272 over 136x is equal to 2. So now that we've found x is equal to 2, we can plug it in to either equations 4 or 5 so that we could solve for y. So plug x equals 2 into 4 or 5 to find what the value of y is. So it looks like equation 4 is a little bit easier to deal with. So let's plug it into 24x minus 2y is equal to 48. So letting x equals 2, we got 24 times 2 minus 2y is equal to 48. And 24 times 2 is 48. Minus 2y is equal to 48. And subtracting 48 from each side, we get minus 2y is equal to 0. And the only way that can be is if y was 0 itself. So now we got x is equal to 2 and y is equal to 0. So finally, we want to find z, right? That's what's left over. So we want to plug x is equal to 2, y is equal to 0 into either one of the original equations. So it's into either 1, 2, or 3. So let's scroll up to see which one looks the nicest to plug into. It looks like the third one has the smallest coefficient, so it might be the least annoying to plug into. So let's try plugging it into equation 3 in this case, right? So equation 3 is 8x minus 7y plus z is equal to 15. So now we know what x is, so x 8 times 2 minus 7 times 0 plus z is equal to 15. 7 times 0 is just going to be 0, so we're left with 16 plus z is equal to 15. And then subtracting 16 from each side, we get that z is equal to 15 minus 16, which is negative 1. So now we have found our x, y, and z, and we want to express our answer in terms of an ordered triple. So our final statement is the solution to the system is the ordered triple x, comma, y, comma, z. So x is 2, comma, y, which is 0, comma, z, which is negative 1.